You hear the term AI thrown around everywhere, right? But what does it actually mean? How do you get from a bunch of circuits and code to a machine that can, actually think? All right, let's dive in and really demystify this whole thing. This is the question that started it all. Way back, over 70 years ago, the legendary Alan Turing asked it, can machines think? And it's a huge question, because it's part philosophy, part engineering. And to even begin to answer it, we first have to agree on what thinking even is. So, to get to an answer, we first need to get a handle on the four main ways people in the field even define artificial intelligence. See, it turns out there isn't just one single definition of AI. The whole field really breaks down into four different approaches. It all comes down to two key questions. First, is your goal to think just like a human with all our quirks, or to think with perfect, cold, hard logic? And second, are we going to judge the machine on its internal thought process or just on what it does, its actions? That gives us this grid: thinking humanly, thinking rationally, and acting rationally. Now, the most famous example of acting humanly is, of course, the Turing Test. And the idea is actually pretty simple. You've got a person, an interrogator, who's typing questions to two unseen players. One is a human, the other is a machine. If that interrogator can't consistently tell which one is the machine, well, the machine passes. The goal here isn't to actually think like a person, just to be so good at imitating one that we can't tell the difference. And the Turing test has some real advantages, for sure. It gives us a clear pass-fail, and it cleverly dodges all those messy philosophical debates about consciousness. But it's also got some pretty big flaws. For one, it only really tests wordplay, not physical skills. And maybe the bigger question it raises is this: why should human intelligence be the gold standard anyway? Maybe true machine intelligence is just something else entirely. And that right there, that brings us to the fundamental shift in modern AI. See, for most real-world applications today, the goal isn't to fool people, it's to build systems that make the best possible decisions. So the focus has really moved away from acting humanly to acting rationally. Okay, so this brings us to the absolute core concept in modern AI. For a minute, let's just forget about mysterious thinking machines, and let me introduce you to the hero of our story, the rational agent. This is the framework, the blueprint, for almost every AI system we build today. So what exactly is a rational agent? Well, to put it simply, it's something that does the right thing. It looks at its environment, and based on what it sees, it chooses the action that is most likely to help it achieve its goal. The key word here is maximize. It's all about making the optimal choice to get the best possible outcome. And this interaction is a really basic loop. The agent, and this could be software or a physical robot, it takes in information about its world through its sensors. It processes that information, and then it does something. It performs an action using its actuators. Just think of your own eyes as sensors and your hands as actuators. It's just this constant cycle: perceive, think, act, over and over. Now, to actually design one of these agents, you need a really clear way to describe its job. You can't just tell a computer, be smart. You've got to define its task and its world precisely. And for that, we use something called the PEAS framework. PEAS is just a super useful acronym. It stands for performance, environment, actuators, and sensors. So before we write a single line of code, we ask these four questions. P, performance. How do we measure a good job? E, environment. What kind of world is this thing living in? A, actuators. What can it actually do? And S, sensors. What information can it perceive? Let's make this real. For an automated taxi, what's the performance measure? A safe, fast, legal, and profitable trip. The environment? That's the roads, the traffic, pedestrians, all of it. Its actuators are the steering wheel, accelerator, brake, and its sensors are things like cameras, GPS, and sonar. And you can see how this same PAS framework makes a really abstract problem totally concrete, whether it's a factory robot or even a simple robot vacuum. Okay, so now we know what an agent is and how to define its job. Now for the fun part. How do we actually make them intelligent? We don't just jump to some super genius AI. We build them up level by level, with each one getting more complex and more powerful. So at the most basic level, level 1, you've got the Simple Reflex agent. You can think of this as the knee-jerk agent. It just runs on simple if-then rules, with absolutely no memory. If the brake lights in front of me turn on, then I slow down. It only reacts to what it sees right this second. It's really fast, but also pretty limited. So the first real level up is a big one. We give the agent memory. A model-based agent keeps an internal model or a state of how the world works, and this is a total game changer. A self-driving car doesn't just see the car in front of it now, it remembers that other car that was in its blind spot a second ago. This lets it deal with a world that it can't fully see all at once.
The next massive leap is giving the agent goals. A goal-based agent isn't just reacting anymore, it has a destination in mind. Your GPS app doesn't just react to the car in front of it, it's constantly asking, will this turn get me to my destination faster? This is huge because it lets the agent think ahead and plan a whole sequence of moves to get to a future state that it wants.
And finally, we get to the top tier, the utility-based agent. So, what happens when an agent has multiple goals that might conflict with each other? Like a taxi that wants to be both fast and safe? Well, utility is basically a way of measuring happiness or preference. It lets the agent weigh the trade-offs and choose the action that leads to the best possible outcome, even when no single option is perfect.
So we have these increasingly sophisticated agents that can remember, they can plan, they can make trade-offs, but how do they actually do it? How do they figure out the best series of actions to take to reach their goal? The answer lies in one fundamental technique that is basically the superpower of almost all AI. At its heart, it all comes down to search. And what we mean by search is pretty much exactly what it sounds like. It is a mental exploration of possibilities. Before a chess program makes a move, it's exploring thousands, maybe millions of possible future game states. That whole exploration process, that's search.
So how does an agent actually perform a search? Well, it makes the problem formal. First, it defines its initial state. Where am I right now? Second, it defines its operators. What are all the possible things I'm allowed to do from here? And third, it defines the goal test. How will I know when I've actually won? Once you have those three things, the problem isn't fuzzy anymore. It's a map of possibilities just waiting to be explored. And you've got to understand, this isn't just for games or navigating a map. Search is the foundational engine. It's the beating heart behind so many different areas of AI. From robotics and planning, all the way to natural language processing and machine learning, the core challenge is often about intelligently searching through a massive space of possibilities to find the very best solution. So here's the crucial takeaway. At the end of the day, when we're talking about AI, what we're really talking about is designing these sophisticated, rational agents. And the intelligence of those agents comes from their ability to build a model of the world, to define goals, and then to efficiently search through that enormous number of possible actions to find the one path that leads to the best outcome. And that brings it all back to your world. Think about the AI you interact with every day. The navigation app on your phone, the recommendation algorithm on Netflix, your email spam filter. Now that you've got the framework, think about it. What kind of agents are they? Are they just simple reflex agents? Or do they have goals and a complex model of the world? It's a really fascinating way to look at the technology that's all around us.